In this video, I want to talk about the voltage divider circuits. So sometimes when we are working with circuits or when we are designing circuits, it is necessary to develop more than one voltage level from a single voltage supply. So one way of doing this is by using a voltage divider circuit. So the figure that you see here is a very basic example of a voltage divider circuit. So we have Vs, positive, negative polarities. We have R1 and then we have R2. So let's just see what are the voltages that we have for R1 and R2. So this is very simple. If we use the Kirchhoff's current law, we know that since all these three components are connected in series, they all have the same current. So the same current that is provided by Vs is going to be going through R1 and R2. So because of that, we need to only apply KVL around this closed loop. So if I use the passive sign convention, what we have is we have negative Vs plus positive V1 plus positive V2 equals 0. Or if I rearrange it, Vs is equal to V1 plus V2. But from Ohm's law, we know that V1 equals the current multiplied by R1. So that is what we do here. So we have V1 equal I1 multiplied by R1. Sorry, I multiplied by R1. The same is true for V2 as well. This is I multiplied by R2. So as you can see, writing the KVL for this simple circuit results in Vs equals I multiplied by R1 plus I multiplied by R2. Or this is equivalent to having I being equal to Vs divided by R1 plus R2. So this is something that you have seen before too when we were talking about resistors in series. If you remember, this is the equivalent resistance of these two resistors being in series. So now that we have this, we can calculate V1 and V2. Why? Because we have the current that goes through each one of them individually. And we know the values for the resistance too. So V1 equals I multiplied by R1. I is Vs divided by R1 plus R2. So this becomes Vs R1 over R1 plus R2. What about V2? The same thing applies here too. This is I multiplied by R2, which equals Vs R2 divided by R1 plus R2. So as you can see, V1 and V2 are fractions of Vs. So how are these fractions calculated? By multiplying the value of the resistor that we want to find the voltage across it divided by the equivalent resistance. So this one is our EQ for both of them. So what happens if the value of R1 is larger than R2? If the value of R1 is larger than R2, between the two, V1 is going to be larger. So whenever we have a larger resistor connected to a smaller resistor, the voltage across the larger resistor is going to be larger than the voltage across the smaller resistor. So as I said, each is the ratio of the resistance across which the divided voltage is defined, divided by the sum of the two resistors. So if R1 is greater than R2, then V1 is greater than V2, and vice versa. So using this simple circuit, we are able to divide Vs into two voltages. But things are not that simple. So even though this is the very basic voltage divider circuit, if you're asked to design a voltage divider circuit, there are other things that you need to consider. So the first thing is basically the values for R1 and R2. But that's not enough. The other thing is the power losses that occur in dividing the source voltages. So do you remember the equation for power was VI? So for example, for P1, so the power at resistor 1 equals V1 multiplied by I. So I was Vs divided by R1 plus R2. So this is I. What is V1? V1 was R1 divided by R1 plus R2 multiplied by Vs. So if I do the calculations, this becomes R1 divided by R1 plus R2 squared multiplied by Vs squared. What about P2? So you can follow the same procedure and find the value for P2 as well. So as you can see, if we want to, let's say, connect the two terminals of R2 to another circuit, because we are dividing the voltage of the original voltage source, there are some of the power that is being dissipated in R1. That is something that we need to take into consideration. So not the full power of the original voltage source will be delivered to whatever we want to connect here. Another thing to consider is that what are the effects of connecting the voltage divider to other circuit components. So let's say if we connect this to an RL, basically a load, right? How much connecting this load in parallel to R2 would change the equivalent resistance of the whole circuit, right? That's another thing that you need to also consider. And finally, what is the sensitivity of the divider to the tolerances or the ranges of possible values of resistors? Because in reality, resistors are not fixed values or are not completely accurate. So you might have a resistor to have a value of 1 kilo ohm plus or minus 1% error. So that means that the resistor can be anywhere between 1010 ohms and 990 ohms, right? So this is what is called a tolerance. So based on this tolerance, you need to do some sensitivity analysis to figure out whether your voltage divider is working properly or not. So to answer some of these questions, let's just take a look at this circuit. So we have this independent voltage source that we want to divide between two voltages. A portion will be across R1 and another portion will be across R2. So V2 and VO are exactly the same, because as you can see, R2 and RL are in parallel. So we want to derive this RL. That is what we call here the load resistance. So if we want to find out how much voltage from Vs is going to be delivered to the combination of R2 and RL, we basically need to do the voltage division analysis. So the voltage division analysis, in the previous slide you saw that if we have two resistors, positive, negative Vs, R1 and R2, so V2, the voltage across R2, was R2 divided by R1 plus R2 multiplied by Vs. So now instead of R2 as a single resistor, we have R2 in parallel with RL. So that means that these two have an equivalent resistance that this voltage source is seeing. So that means that this equation needs to be modified to this. So VO or V2 is going to be equal to Req, the equivalent resistance of R2 being in parallel to RL, divided by R1 plus Req. So similar to this that we have here, but instead of R2, now we have Req, the equivalent resistance of R2 in parallel to RL, multiplied by Vs. What is the equivalent resistance for R2 and RL being in parallel? We saw it in a previous lecture that it is the multiplication of the two divided by the sum of the two. So now let's just replace this in the above equation. So we have VO to be equal to R2 RL divided by R2 plus RL. That is the numerator. In the denominator we have R1 plus R2 RL divided by R2 plus RL multiplied by Vs. So this is the equation that we have. So can it be any simpler than that? Yes, by some algebraic manipulation we can get to a much simpler and more representative equation. So the simpler equation that we have after doing the manipulations, I leave that to you. So we have VO to be equal to R2 divided by R1 multiplied by this factor plus R2. So again, this equation is nothing new, right? Simple manipulation of the previous equation would give us this result. So now what we see here is that we have R2 over RL. You remember when we were doing the analysis of two resistors being in parallel, and we said if one of them is larger than the other one by several orders of magnitude, what happens? So the same analysis can be applied here. So as long as RL is much larger than R2, so if RL is very larger than R2, that means that R2 over RL, you can consider it to be very close to 0, which means that 1 plus R2 over RL is approximately 1. So if that happens, R1 multiplied by 1 plus R2 over RL plus R2, that is approximately equal to R1 plus R2, which makes VO to be R2 R1 plus R2 Vs. So approximately. So what was this equation for? This equation was the same equation that we had if we only had R1 and R2. This one is R2, this one is R1. So the voltage across this V2 was equal to R2 over R1 plus R2 multiplied by Vs. So when RL is several orders of magnitude larger than R2, this circuit and this circuit are practically equivalent. So where RL is very, very larger than R2. So when this is the case, the voltage ratio VO over Vs is essentially undisturbed by the addition of the load resistor. So that's one of the things that you need to always consider, that when you are working with voltage divider circuits, when you connect the second part of your circuit to the first part, to the voltage divider, you have some loading effects that basically alter your calculations. So to ensure that these loading effects are very small, it is beneficial that the load resistor is much larger than R2. If it's very large compared to R2, that means that by connecting the load here to your circuit, to the voltage divider circuit, you are not altering the calculations of the voltage divider circuit. So now, based on these, we can generalize the voltage divider circuit. So how to generalize the previous simple two resistor voltage divider circuit? So let's just say we have this circuit, and this circuit, whatever it is, gives us a voltage across its two terminals. So these two terminals are now connected to a bunch of resistors. We have R1, R2, all the way to Rn. Now we want to see what is the voltage across resistor Rj. And you see all of these are connected in series. So what would be the voltage across Rj? The answer to that is very simple. You need to do KVL in this closed path. So if I do that, we have negative V plus R1I plus R2I. You see, since all of them are connected in series, the current that goes through them is exactly the same. Dot 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 plus Rj multiplied by, this one is Rj multiplied by I, plus Rn minus 1 multiplied by I, and Rn multiplied by I equals 0. So based on this, what is I? I is V divided by the sum of all the resistors, or the equivalent resistance of the resistors connected all in series. So now that we have this, so let me just quickly write it like this, Req. So now that we have this, what is the voltage across Rj? So Vj equals I multiplied by Rj, or Rj over Req multiplied by V. So this means that this portion of the initial voltage will be across Rj. What portion will be across R1? So V1 becomes R1 divided by Req multiplied by B. What portion is across Rn minus 1? So Vn minus 1 equals Rn minus 1 over Req. So this is multiplication. So considering the Ohm's law and using the equivalent resistance, we can have I, the current that goes through all these resistors, to be equal to the voltage across these two terminals divided by R1 plus R2 all the way to Rn. So this denominator is the equivalent resistance of all these resistors in series. So I simply is the voltage divided by the equivalent resistance that we have here. Now, since we know the current that goes through these individual resistors, we can easily use Ohm's law to find the voltage across each one of the resistors individually. So Vj, the voltage across resistor Rj, equals the current multiplied by Rj, or it's equivalent to Rj divided by the equivalent resistance multiplied by the voltage across these two terminals. So in this video, you got introduced to voltage divider circuits, and also you saw how we can generalize the simple two resistor voltage divider circuit into having more resistors.